All right, let's get started. So today we're going to finish up classification, and in particular we're going to talk about Newton's method and how we use that to solve classification problems. Though I'm introducing it here in terms of solving these classification tasks, Newton's method is actually a pretty general algorithm for finding zeros of the function. As a root finding algorithm, right? It takes some function and it'll find some value that gives 0 for that function. And that's actually a very general technique that we can use in a lot of domains. And I'm going to spend some time on it because though we're going to use it here just for solving, for example, these classification tasks with logistic regression, in general, we're going to use Newton's method to solve a lot of other problems too. Like, for example, when we talk about power flow analysis. So this is now, in a few lectures coming up, we'll talk about the physics of electricity and how actually power will flow in an electric network. And it turns out, though, it's a very different problem, of course. We're going to use Newton's method, the exact same algorithm, to solve that problem. So these things are very general, and it's really useful in a lot of cases. I'm going to briefly talk about the extension to the nonlinear setting of classification methods. Remember, a lot of our work in regression was about how do you extend these linear models to the nonlinear setting by introducing kernels or introducing features and these kind of things. And I'm going to talk about it pretty briefly here because really the framework is exactly the same. You just take your feature vector. I mean, everything we've been talking about still for classification is still in terms of feature vectors. And so you just construct a nonlinear feature vector. Or say you use a kernel instead of just a linear feature vector. So I'll mention that and kind of show some pictures here, but we won't talk about it very long. And then hopefully we can get to a good chunk today about evaluating machine learning algorithms. So we've talked a lot about sort of solving things and optimizing loss functions and parameters and all that. But what really matters in a lot of application domains, of course, like the ones we're talking about with energy, is how well these things actually work in some sense, right? Is this getting good performance or not? And we really haven't talked about how to evaluate that at all yet. I mean, I've shown some graphs of things kind of overfitting a little bit and things that might look bad, but we haven't formalized how you actually go about determining if performance of an algorithm is good or not. And how do you also go about reporting that? If you want to write a paper, how do you actually report the performance of the algorithm? So there's several topics within this, but hopefully we'll get to that for a good chunk of today. A few general notes that I want to mention before starting, though. There were a couple next week, I'm going to have 2 office hours because the homework's due on Thursday. So I'll have office hours both Monday and Wednesday, and I'll send out an email about that. If you can't make them, also email me. I can set up sort of an office hours separate from that. You can just come in at some point, maybe for a shorter time. I know that there's oftentimes classes on Mondays and Wednesdays. People have classes both those days. So if you do have classes, then please let me know, and we'll find a time that works. The other thing, okay, so I did get a couple questions on the homework about the computing some of the kernels, this square dist function, sqdist. Someone mentioned that they couldn't find it or something like that. That function, square dist, is not a built-in MATLAB function, but it's included in the data for the first homework. So you should have that function in the data file you download for the first homework. One other thing, right. One other person mentioned asked about textbooks for this course. So there's obviously no textbook for the course. And part of that's really because this course covers a lot of things. I mean, we've been talking about machine learning so far, but really we're almost done with machine learning. And then we're going to move on to power systems. Then we're going to move on to control. And so because of that, there's no really one textbook that covers all these things. I try to make the slides self-contained so that everything you're going to have to do in the homework is described in the slides. And if you do want to have some more textbooks, I put a few links to textbooks that cover in total some of the various topics we cover in this course. I don't recommend, I'm not suggest anyone go out and buy them all. But if you happen to be curious and you want to pursue an area in more depth, there are books that might come in handy. I think that was all I had for administrative things. Were there any questions about the homework? It's been out for a week now, so if there are any kind of general questions about it, not specific things we can talk about in office hours, but if there are any general kind of questions about the format or about the procedures, anything? Yeah.
So when we use the kernel approach for the optimization,
Uh-huh.
we don't really care about theta value.
Right. So in kernels in general, theta could be infinite dimensional, right? So theta is only really constructed in general for kernels through those alphas, right? So remember the form of the kernel that we had that was kind of key was that theta equals phi transpose alpha. And so while we're not really representing theta ever, we're kind of representing it by computing the alphas. So we're representing it implicitly. And that's,
Really know the model shape.
yeah, you can't ever really know the real thetas, right? Because they could be very high dimensional. They could just not be representable. If you're sort of asking about the intuition of, can we get intuition from this model? You can in certain senses by looking at the alphas instead and seeing what those alphas, they essentially give, in some sense, kind of weights to different examples in your training set. And so that can give you intuition, but I actually will caution you against pursuing that too deeply because I do want to kind of highlight the fact that we are ultimately constructing a feature vector here. It's just you can't represent that exactly.
Can you interpret any single alpha value in
You can. They have to do with assigning weight to certain training examples. So if all your training examples, if the alphas for all of them were 0, for example, and 1 had a weight of 1, that would mean essentially you're only looking at that one example to construct your feature vector. I mean, of course, it's not obvious either because it can be positive weight or negative weight, and they can have all these kind of different features here. But that is sort of an intuition you can get. Maybe we can chat about that at office hours or after class. OK, so let me jump back into Newton's method here. So remember, Newton's method is a way of having some function f is a function from Rn to Rn. And the important part here to note is that f takes vectors as inputs and outputs vectors of the same dimension, right? And we want to find some z such that f of z equals 0. And when I say 0 here, I really mean a n-dimensional vector of all zeros. I'll often use 0 to represent a vector, and you have to figure out what size it is by the rest of the notation I'm using. So in the 1D case, this is a very simple update. It's just the update is z. This arrow here, people have seen this before. It means assigned to. So when we talk about an algorithm, we talk about equations, talk about things being equal to each other. But to say z equals z minus this is sort of, that only holds when this is sort of a fixed point here. This is kind of defining an algorithm, right? So the algorithm is we assign z to be the value of z minus f divided by f prime of z, where f prime now is the 1D derivative of f, because we're talking about 1D functions here. So what's important in our setting is the extension of this to the multivariate case. And who here has actually done Newton's method in the multivariate Newton's method before? Just by a show of hands. Are there people that have? Okay, only a few. OK. Who's done it in the 1D case? I saw this in the calculus course at some point. OK, some more, but still not everyone. So it's good to kind of get an intuition about what this method is doing and why this procedure finds a 0 of the function. And that was sort of the graph I showed you last time about kind of constructing a approximation in the function that hits the 0 axis, and then you jump to that point and you keep updating. OK, but now let's talk about the extension of this to the multivariate case. Now we're going to go to our setting here where f is the function that maps Rn to Rn. And the important quantity that we'll need to define is something called the Jacobian of a function. When you go to multivariate calculus, there's lots of things like gradients and Jacobians that are all kind of very similar, but there are subtle differences here. So remember, the gradient of a function, I'll try to keep these kind of categorized well. The gradient of a function was defined for functions that take as input a vector but output a single real valued number. So the gradient is defined for f, which maps from Rn to R. Right, because the gradient was a big vector of all the partial derivatives. So basically it was the gradient with the z of f of z equals the partial derivative with respect to f of the f of z1, partial with respect to z2, etc. Right? And this notation here, the partial of f with respect to z, really only makes sense if f is a single output, right? Then you're taking derivative with respect to a single output. For functions that have multiple outputs, so vector valued functions, we need a little bit different notation. And I'm going to use this notation because it's what's common. It's sort of leads to some confusion when you talk about the difference between a gradient and a Jacobian. But essentially, the Jacobian is just like the gradient, but it's defined for values that have multiple outputs. Sorry, functions that have multiple outputs. So the Jacobian, sorry, writing G again. Is defined for functions that take a vector as input and output another vector. What this is a matrix of all the possible partial derivatives of every element of that function and every input. And in particular, we're going to call this Jacobian dz f of z. And the ij element here, and let me make sure I get this right here because I always mix these up, is the derivative. So the ith row in the jth column is the derivative of the ith output of that function with respect to the jth input. And this is writing it here just as a big matrix. So the reason this is a little bit confusing is that the Jacobian, when you have a function, I mean the Jacobian is actually defined for any function here, Rn to Rm. Sorry, I should have clarified that. Newton's method will be defined for mappings here. Jacobian is defined for any mapping f of Rn to f of Rm. And if m happens to be equal to 1, then the Jacobian is actually the transpose of the gradient. So essentially, you can think of each row vector of the Jacobian is like the gradient of that function with respect to, the gradient of the ith output with respect to the input there. If that's a little bit confusing, don't worry about it. These are all the definitions you have right here. These definitions are kind of the formal definitions. Actually, maybe I'll even put up this. I guess this is the formal definition right here. Maybe I'll put this into the slides just to give the complete definition. This kind of just does it element by element. It might be a little bit confusing. I think it's also probably, yeah, no, I think that, right, yeah, so this is maps to that notation there. But essentially, because Newton's method deals with functions that take n inputs and outputs, we need to have some function that's more expressive than just the gradients themselves, because gradients are really only about real valued functions. Now, given this, remember, Newton's method was just z is assigned to z minus f of z over f prime of z. That was for the single variate case. With this notation of Jacobians, and part of the reason why we define it like this, as the gradients being row vectors here, is that Newton's method takes on a very nice form here. So Newton's method in the multivariate case is just equal to z takes on the value of z minus this Jacobian inverse times the function itself. Oops. Oopsie. So let's just check this all makes sense here. So the Jacobian in general is an m by n matrix. When you have functions that map from Rn to Rn, the Jacobian will therefore be an n by n matrix. The output of the function itself will be an n-dimensional vector, and the input will also be an n-dimensional vector. So this is an n-dimensional vector, this is an n by n dimensional matrix, this is an n-dimensional vector. So all the units here make sense, and you can compute these terms term by term. But it's important to remember that this is an n-dimensional vector, this is an n by n dimensional matrix, this is an n-dimensional vector. And really it's just like this, right? I mean, because the inverse is just kind of like, I mean, this is just the, in the case of a 1D function, the inverse would just be dividing by the inverted Jacobian would just be like dividing by the gradient here. Okay, so this is a method, remember, that lets us find zeros of a function. Right, that was the golden method in general. What we want to do in the case of optimization is find a input point where the gradient of our optimization objective is 0, right? So remember does everyone sort of can I erase this? I have very little writing space that I want to try to get it all in the video, unfortunately, but hopefully it's there for posterity, I guess, on the video itself. So remember, our goal is to minimize over theta of, and I'm going to call it just j of theta here. I used that notation a little bit before, which is equal to the sum of from I equals 1 to m of the loss of our predicted value and the real value. Our predicted value, remember, is just going to be this theta transpose phi of x. So this was just the notation we used last time. What we showed, or what we talked about in the least squares case, is that our goal then really is to find a point, find theta, such that the gradient with respect to theta of j of theta equals 0. Where again, this 0 here means a vector of zeros. So now this could be, in the case of least squares, this was kind of nice because this was just sort of a simple expression that we could easily invert. In the case of logistic regression, this is no longer a simple expression. And I'll write it in a second. It doesn't really matter the exact form of the expression there. But for these other loss functions, this expression can no longer, even when they're differentiable, this expression can no longer be kind of nice and allow us to directly solve for theta. So we're going to use Newton's method to find a point where this holds. And that's how we're going to solve these type of problems. One more bit of notation here, just for convenience. We'll actually, so basically we want to find the Jacobian of the gradient, right? Because we need to differentiate kind of twice. Once to find this gradient of the cost function, and then once to find the Jacobian for Newton's method. And this kind of weird term, right? The Jacobian gets kind of nasty, right? So the Jacobian of the gradient of j of theta, this is kind of nasty notation here. So we just actually call this oftentimes the Hessian of the function. So the Hessian equals, I'll use this second kind of gradient term here to denote the Hessian. And that's described on this page. So again, we're going to use the method to find a z such that the gradient of the function equals 0. And to do this, just for convenience notation, we'll actually define something called the Hessian here, which is just the Jacobian of the gradient. But kind of even sometimes more intuitively, you could think of it as just the ijth element of the Jacobian, sorry, of the Hessian. equals the second derivative of our original function. It should be j. Second derivative of our original function with respect to the I and j entries. So it's essentially a matrix of all possible second partial derivatives of this function, is all it is. And Newton's method then is just very simple. We just take z equals this term, which is our Jacobian, but now it's the Hessian, inverse times our function, which we want to try to get to a 0, which in this case is the gradient. So Newton's method is just this form exactly. We repeat the following: z equals z minus the Hessian inverse times the gradient. Now, if you've seen this method before at all, you may know that this does not always succeed. And sometimes you actually have to kind of scale this update a little bit. But we won't worry about that here. We'll sort of think about it conceptually. This is conceptually the update that we're doing. And for all the cases you'll deal with in the homework and in the cases I'm going to show in the slides here, this update alone is sufficient. So does this basic strategy make sense to everyone? Big picture, we're trying to find a 0 of the gradient. We do that through Newton's method, which takes this form, and we call this the Hessian, which is the Jacobian of the gradient. And it's good to, those are the only 3 terms you're really going to have to know for vector or for matrix calculus. They're also, at least the Hessian and gradient are described in those lecture notes on linear algebra. So you can read up on those too if this is all seems a little bit confusing or abstract. Yeah?
On the last slide, I think you had you didn't have a gradient of f of z.
Right. So in the last slide, we're talking about finding a 0 of f. Right? So we're talking about f being a function mapping from Rn to Rn, and you want to find a 0 of it. Here, Newton's method is talking about finding a point f, and I probably should have used j here instead of f, because it might make things a little bit clearer. In this slide, I'm implicitly saying that f is actually a real value, a function that maps from Rn to a real valued number, and we're optimizing it here. Maybe actually that, and that's what I wrote here, but maybe it's actually much better to write j there rather than f, because I'm switching from notations. But you're finding a 0 now, not of the function itself, but of the gradient of the function. And that's how you optimize the function. And also, incidentally, the way that YALMIP will internally solve a problem is very much along the lines of this type of approach, actually. It's significantly more complicated because they have constraints and things like this, but it basically is Newton's method. All right. So let's talk about how you actually apply this now to logistic regression and how you can actually solve that with Newton's method. I'm not going to go through these derivations in detail. I'll sort of give some idea about why these gradients and Hessians are the way they are, but we actually don't really care about that right here. The point I just want to make is algorithmically, how does this all work? So in logistic regression, J, remember, that we're trying to optimize, is the sum, I equals 1 to m, of this logistic loss function, which is 1 plus exponent of negative theta, or negative yi. Yi times theta transpose phi xi. And if you work out the terms element by element, it turns out that the gradient and Hessian have this form. So the gradient is equal to phi transpose times a diagonal matrix Z, where the diagonal entries of Z are just given by this, times y. And to see why this might be the case, I don't want to go through this in a lot of detail. If you want to work this out, you can drive it on your own. It isn't too much math. But for example, to find the gradient here of this whole thing, well, we know the gradient is linear. It's one of the things I first sort of talked about as a function of the gradient. So we can push the gradient within the sum. So we can sort of, if we want to take the gradients here, we can push the gradient within the sum. When you have gradients of kind of functions of something, and these functions are 1D functions, then gradients act just kind of like derivatives. And so you can use things like the chain rule and other things you learned in calculus in the same way. So the derivative of a log of something is equal to 1 over that thing. So the gradient here is going to be 1 over this, 1 plus x negative y I times theta. This is sort of just actually incidentally for if you're curious about this. I'm going to do it very, very quickly. And I expect you to know how to do this. So that's what happens if you take the derivative of a log. The exponent, derivative of an exponent is just the same thing. So we're going to put another exponent up here. So exponent of negative y I c dot times that. And then the derivative of this thing, the gradient rather of this thing, well, that's just going to be yi or negative yi times phi of xi, right? And now this term you can actually simplify by multiplying, by basically multiplying and dividing by this guy here. These terms cancel out, and this term here equals that zii term. And then you have the yi term, and you have the phi of xi. So that kind of looks like this. Hopefully that makes a little bit of sense. If it doesn't, really don't worry. Basically, that looks like one element of this thing, or one element in the sum of this thing. And then you sum over all of them, and you get a nice vector form like this, just that. If you want to go through that, I mean, this is not at all required to know. I'm just trying to give people that might be curious a little idea about why this might be the case. But just you can take it from me for now that these are the Jacobians and the gradients here. So now the actual code for Newton's method is pretty simple, right? So here is the MATLAB code that will actually solve this using Newton's method. OK, so the function, which I'm calling log reg, takes as input our features, phi, the true outputs y, and it will output a theta that minimizes the logistic loss function. And we just go through it line by line. So I'm just setting up sort of the vector here. We initialize theta to be 0. Doesn't really matter what you initialize it to be. I guess 0 works well oftentimes. If you initialize it to be too big, you might have these problems with Newton's method, maybe not working all that well. So 0 is a pretty good initialization point. When I say not working well, I mean you need to kind of temper those steps. So we won't worry about that case here, though. So theta is equal to all zeros. The g is just the gradient, but I'm setting it to be equal to 1, so this will not quit the first time. But basically, here I evaluate those z's, those zii terms, right? This is just a little bit nicer MATLAB form for evaluating that gradient here. Rather than multiply by a diagonal matrix, I just multiply element by element, z times y. And that gives us the gradient. And you can sort of switch between those two if you aren't quite sure about how exactly that matches up with what we saw before, but it does. This computes the Hessian in the same way. This computes the Hessian matrix that you saw in the last slide. And then the update is just theta equals theta minus h backslash g. For square matrices, h backslash is just like the inverse. So this is just in the inverse of h times g. And that's exactly kind of the updates that we saw for Newton's method laid out in the previous slides. And this is just the code here. Now, what's nice about this, and why would you actually want to do this if you already have YALMIP, and so you can just type in, minimize exactly this thing, or solve SDP with this thing typed in. And the reason is that, well, first of all, internally, YALMIP is doing something very similar to this, but maybe you don't really care about what it's doing internally. But the reality is that for a lot of problems, YALMIP can be quite slow. And doing this explicitly will actually be much, much faster. So on my computer, for example, using about 300 examples and only a three-dimensional problem, YALMIP took something like 20 seconds to solve it, which is a really small problem, right? Dimension 3 problem. There are 3 parameters we're learning. And YALMIP still took 20 seconds or 21 seconds to solve it, whereas this code here solves it in a hundredth of a second. And it actually could be a lot faster than that if I optimize this even a little bit more than I'm optimizing it here. But I'm trying to make it somewhat readable here. So you can do even better a little bit. But basically, this is a huge difference, right? And this is not uncommon for custom routines like this when you have objectives that are, in some sense, easy to optimize because they're differentiable, they have all these nice properties that we can use the Newton's method exactly. Oftentimes, code you can write like this will be much faster than a general purpose library like YALMIP. So YALMIP is great for testing things out, but as something to actually sort of use for your big final production system when you have a lot of data, it'll have some issues there. The last thing I want to mention is that the same also goes for SVMs, support vector machines. So remember, I said support vector machines were just like everything here, but with the hinge loss function instead of this logistic loss function, which looked actually very similar, but it was different. Here, just like with the absolute loss function, it's actually harder to optimize this directly. The way you typically do it is form it as a constrained optimization problem, just like we did for absolute loss. And that makes the SVMs sometimes a lot harder to write custom MATLAB code for. However, there are lots of libraries, libsvm and svmlite, just to name a few, which you can just Google and download, that will solve this for you, solve similar problems just for an SVM for you, and do it very, very fast. So code out there exists to do it fast. You can solve kind of medium-sized problems just by writing them out using YALMIP. And for bigger-sized problems, you can download these packages here and solve it with those things. OK, so that's all I'm going to say about this bit of classification before moving on to nonlinear methods. Are there any questions about this? This was sort of a whirlwind, I know. I think this method will probably make more sense when you've seen it in 2 different settings, both the optimization setting and then the solving, say, power flow equations for power systems. And we'll sort of cover both of these and try to keep things consistent between the 2 notations. All right, so one quick little bit now. Oh, actually, let me just also show you. One nice thing about Newton's method is that when it works in situations like this, and when you can always take those big steps without ever having to kind of scale down the update, it can work really, really fast. So remember, we could not solve logistic regression analytically, but it ends up taking about usually 9 iterations or so for small problems to find a solution, or rather for this problem. This was our classification task. Remember, we're trying to separate 2 different refrigerators from each other. For this one, it takes, here's the first iteration. So after 1 iteration, it already is pretty good. Here's the second iteration, the third, et cetera. And here's the last one. By 10, it's not going to get any better. It's at machine precision. So here, then, is actually a graph also of the how big the gradient is, the norm of the gradient versus the iteration number. And you start out, remember, with theta equals 0. And so that's a pretty big norm because you're doing pretty badly at that point. But very, very fast, this starts decreasing. This is a log scale here, notice. So it's linear on the iteration number, but logarithmic here. And this is very, very fast convergence. It's known as quadratic convergence, for those that have heard that term before, because it's actually faster than linear even on a log plot like this. It's actually quadratic here. So very, very fast. 10 iterations, and you've solved this to the value that a machine can handle. So we essentially have solved this problem, even though we can't solve it analytically. All right, so last thing is just the nonlinear case now. And I'm actually not going to say much at all about this because it's the exact same thing as for as for regression. So just like with regression, there were times when a line through the data didn't quite cut it, right? So we're sort of think about linear regression. Purely linear regression is just kind of fitting a line to data. And so we wanted to use nonlinear features or kernels to come up with more expressive functions. And we can do the exact same thing for classification here. And here is the plot of another classification task. It's fairly similar to the old one. The old one, remember, was just here are two refrigerators, tell them apart. What's maybe more interesting in a house is not just because there might not be two refrigerators in the same home. It might not be that common that you have two that are the exact same one. But maybe a more interesting thing would be, well, figure out what's a refrigerator and what's everything else in this home. Tell me when the refrigerator comes on, distinguishing it from every other thing in the house. And here is sort of a plot of the refrigerator and then every other device that comes on in the home in terms of this duration and power features that we had, or power, duration and power inputs that we had. So as you might expect, it's sort of a trickier problem now, right? Because now there isn't just like there's one cluster here for the one fridge and one here for the other fridge. There's really points, other devices sort of lie a lot of other places around here, right? So devices might have some more power, some more rare devices here. There's clearly some kind of clusters here of one device that has this power, it stays on for this long, one maybe here. And so you kind of want, a line really wouldn't cut it here, right? If you just drew a line through this plot and said that everything on one side was one class, everything the other was a different class, that would be a pretty bad model for what's going on here. Instead, you really want some notion that things kind of in this area are going to be refrigerator and things outside of it maybe are going to be everything else. Maybe with the, maybe there's actually two spots for the refrigerator. So I'm not showing it here, but this fridge actually also has a defrost cycle, which uses a lot more power, and so there's actually another little point way off here. It's also the same fridge. And so you probably want to use to sort of model both those things and be able to capture kind of these general functions like this. So what's nice now is that everything is exactly the same as for the regression case. We can do that. We can model these functions, again, just by using kernel, just by either A, putting in nonlinear features here, or by using kernels again. And for kernels in particular, the trick is just, again, this statement that the features equal, sorry, that the thetas equal the features times these alphas. And so here is just some quick code that actually does it. Here is a kernelized version of a support vector machine. So remember, the support vector machine minimized over theta, the sum from I1 to m of this hinge loss term, right, which was the max between 0 and 1 minus yi times theta transpose b xi. And then also at the end plus, not in the sum, but plus some regularization usually put in on theta. So let's think about this in terms of the kernels now. Well, this term we can just write out as the sum of all these kernels, right? This term is going to be this, and we're going to be alpha transpose c transpose alpha, which is equals alpha transpose times the kernel matrix times alpha. And so doing a few more substitutions to this guy here, you can actually put this in a form that is just, first you have your regularization term here, which is your effective norm of theta. So here it becomes a norm where you multiply alpha times k times alpha. And then you have this hinge loss term written right here, just in matrix form. And you can sort of check to make sure that this is actually doing the same thing as that is element by element. So again, this is just the basic idea. you're mainly going to talk about nonlinear methods in the homeworks at least. You'll mainly deal with them on the regression case, just because we talked about that a whole lot. But the point is, you can do this exact same thing in classification, because we really had the same form for our functions, right? We set up loss functions that were linear in parameters. The prediction was linear function of the parameters, and we had some loss function based on that, and the true output. And so because we had that kind of same framework, you can take the exact same methods and make them all nonlinear. And just to give you some idea of what this looks like, if we use a Gaussian kernel and run a support vector machine for this problem here, we can get boundaries that look like kind of like this. So what I'm drawing now is the boundary of where this classifier changes from saying things are negative to saying things are positive. So everything in the red region here is where it would classify as being positive, and things in the blue region are negative. Actually, I forget which convention I was using for which was the positive, which was the negative class. Well, let's just say the fridge is the positive examples. Everything else is negative. So this just shows kind of the contour plot of everywhere in that area is where it classifies it as being positive or negative. And just like with regression, you can have, and actually I'll also mention what's really happening here, right, is that there is a 3D function, and I'm just plotting here where that function is 0 and where it's positive and where it's negative, rather. And just like with linear regression, if you start getting too fancy in your features, say adding too many features, or say you pick a too small of a bandwidth for those Gaussian kernels, you can start overfitting the data. And if we do that here, we get things that look like this. This is a SVM with a little bit smaller bandwidth. And you can see it kind of it starts sort of fitting this exact shape well, but also kind of weirdly in some ways, right? Because I mean, it's what it does, but it does make kind of weird choices here, seemingly too, where it, why does it put that one in there, and not other ones in there? It's hard, of course, to sort of, think about it intuitively, really, because these points depend on really kind of Gaussians around, or RBFs around every single point in the space with this Gaussian kernel. Don't worry too much. Just know that the smaller bandwidth of the Gaussian kernel can lead to things like this, where you have this kind of overfitting pattern. Okay, so that's all I'm going to say about the nonlinear case for classification. Really not because it's not interesting. It is very interesting. You really would want to have functions that can capture things like this, of course. But it's also not that different from the linear regression case, from the regression case. So we'll just sort of say everything that I talked about before with kernels and all that kind of stuff just stands without any steps. Okay, so that's it for the two big parts of our kind of machine learning, the algorithmic parts at least of our machine learning section of this course. But there's one more very important part of machine learning, and that is, how do you actually now say how good things are really doing? I mean, there's a sense in which, okay, this looks good. I guess this is sort of a nice model here. How good is it really? Is this one better than this one? How do we know which one's better here? And also, when you write a paper, how should you present those results? If I say I ran an SVM and it got this accuracy, where do you come up with that accuracy number? And how do you actually derive that? So that's going to be and this is a hugely important topic. It's a topic that actually is, even in some big papers, is still, even some machine learning conference papers, is still done not quite correctly. So it's good to talk about how this can and should be done, and how we should evaluate methods. Okay, so let me switch slides here. Are there any questions about this before I move on? I imagine there probably are some questions, so please do come to office hours. The homework is not yet about classification. That will be on the next homework, so you don't have to worry about it quite yet, but I want to still keep it in mind. It's something you'll probably want to learn at some point. Say for the next homework. All right, so fortunately, this next bit is a little bit less mathematical. There is some probability that we're introducing here, but it's very basic probability. So a little bit more conceptual than some of the mathematical stuff we did before. And the questions really are, there are a couple questions. I think basic question is, how do we evaluate methods? How do we tell if something is achieving good performance or not? And there may be a few reasons that we want to ask that question, right? We might want to know, how do we sort of tune those parameters of our method, not the thetas, but things like the lambda, that regularization parameter? How do we know what features to pick? I mean, I could give you intuition about how too many features might overfit, but too few would underfit. But how do we actually do that in a more systematic way? How do we choose what kernel to use? We have many different choices of kernels. How do we pick between all these different things? That's kind of one question we might want to say, well, we should pick the one that performs best in some sense, but how do we know what performs best? That's why we need to know how to evaluate methods. And secondly, and this is the question, and this is the thing that really is again, not always done right even by professionals, is how do we, and I'm guilty of this as well, I should add, I'm not above my own criticisms here. How should we purport the performance of algorithms in papers? Again, sort of in the ideal case, sometimes hard to purport them exactly how we're going to describe here, but in the ideal case, how should we talk about performance of the algorithms? This is something that for some reason is not covered that often in courses on machine learning, for example, and it's really, really important. Just a basic presentation here can really, I think, help a lot to make your presentation of your results, or just the way you present your numbers, much more scientifically sound. So these are the questions we have right now. And the basic question, right, is, well, how do we know if an algorithm is performing well? What does good performance mean for a machine learning algorithm? Now, what I talked about this whole time, in some sense, was the framework I used was this loss function, right? So I said that we have some loss, some j of theta, which is the sum of the different loss functions, and that's in some sense how we're going to evaluate whether something is good, right? If we're low in our loss function, that means good. In fact, we pick our parameters to make this as small as possible. So that was kind of our criterion for performing well. So why don't we just use that criterion as what we pick to evaluate our algorithms? But that was kind of very intuitive. Let's just use that loss function. But also, hopefully, equally intuitively, is the fact that this doesn't always work. For example, if you have a regression task and you want to know what features to add, what features should you use on this task? If you just look at the loss function, it turns out that adding more features will always decrease your loss function. Right, and it has to, because we're picking the parameters theta that minimize that thing. And if we could get it to a certain value with n features, or k features, we could get it to only an even lower value with k plus 1 features. We couldn't possibly do any worse on our sum of loss functions if we add more features. And we have to take this to the extreme case where, imagine if your outputs were random and you had random features. This is not a task you should be able to solve. But for reasons of linear algebra that aren't too hard to show, if you have as many features as you have examples, you will always be able to drive that loss to 0. Essentially because some combination of the features can always exactly give you any output that's of dimension m. And this is just sort of the code that illustrates that. So this is just for the linear regression case. The same thing holds for classification, I should add too. But just sort of to remember, our linear regression was going to be C transpose C inverse times C transpose Y. And if you think about what happens when C is equal to, sorry, when M, the number of examples we have, is equal to K, which is the number of features we have. Well then, these matrices are M by K matrices. You can actually start inverting them individually now. They become invertible themselves. A lot of things cancel, and essentially, maybe I actually won't go through. Well, let me maybe go through it. So remember, our prediction on our examples is going to be C times theta minus Y. That's what we're trying to optimize, right? Let's start thinking what happens when C now is M by M. So it turns out that now, because this is M by M, you can actually push this inverse inside here, just from some basic sort of linear algebra manipulation. You can actually, and we'll do the actual order, but do something like, whole thing, inverse, it would be C inverse, so sorry, this is C. So it would be C inverse, C inverse, transpose, so right like that. These things will cancel, so you have this equals C, this thing equals C inverse Y. Now, this then equals C inverse Y minus Y. So basically, if these things are all invertible, then everything just cancels out. And your predictions are always exactly equal to Y. That's the big thing. Sorry, I wasn't trying to break it out, so it was a little bit floppy. But the basic idea is, when you have enough features, you can always get zero error or zero loss. Okay, I raised that because actually picking these is really cool. So what's a better thing to do instead? And it's something you probably have heard about before, so it probably is no surprise, but the basic idea here is we're going to split our data into two chunks. One's going to be the training set, and one's going to be the training set. Our problem in some sense is that when we talk about loss, the way I talked about before, we're picking our parameters to optimize loss over those examples. So it's not a great kind of criterion, because if you have really expressive features, you can drive that loss down really, really low. What kind of really matters in some sense is not how low is that loss on the examples you saw, but how low is that loss on kind of a random example that's still in your same problem, right? What you care about is not how well can I possibly predict those exact high temperatures, those exact demands from those exact high temperatures. It's kind of a boring problem because you actually know the answers already. So to say you can get 100%, you can just sort of study the exact data you have and you can get perfect accuracy. So the question is, if I'm giving you a new day, what's the loss going to be on that new day when I give you some high temperature and you want to predict temperature? Right? Or if I gave you a new appliance that had some duration and some power level, is that a refrigerator or not? That would be the question you really want to answer. And a way to simulate that in some sense is to divide up our data set into two different data sets. So we're going to talk about a testing set, a training set rather, which is what we talked about before, and I'm going to this is what I mentioned before, and I'm going to just the same way as before, call that xi in Rn and yi for regression, say, in R. Then we have a separate testing set, which is a different set of examples, which I'll call here xi prime in Rn and yi prime. And I'll say that here I equals 1 m, and here I, we have, say, m prime of these. So we have m training examples as we did before, and we have m prime testing examples, just to make the notation kind of concrete. So the way that we actually evaluate methods now is that in the training phase, we do exactly what we did before. We just minimize, and this argmin just means the actual theta that minimizes this whole thing. So we minimize over theta the sum of these losses on the training set here. Remember, xi and yi without a prime are on the training set. For evaluation then, to evaluate performance, we're going to look at the loss again. Oops, I messed up a sum there. It's supposed to be a sum. So the average loss is the average over all the examples of the loss now on the test set. Let me just write that out. So average loss, like I messed the typo. So average loss equals 1 over m prime times the sum from I equals 1 to m prime of our loss between our predicted value, which again is here, just the theta star we computed here, transpose b xi prime and yi prime. And this is a much better evaluation of how this method is performing, because these are examples where we did not explicitly minimize our parameters using those examples, right? They're other kind of randomly drawn examples in some sense. I'm using random, they're very kind of informally. And this is kind of what really matters to us. How well will we do in a random example? And this is a way of simulating that with two different steps. We also call sometimes this average loss on a test set, we call it generalization loss, generalization performance. Yeah? So it does, yes. The idea that you want to do is you want to select it in a way that is as random as possible. I think I actually have the next slide, so let's turn it into the next slide. So, exactly. You need to select the training set and testing set. And these should, in some sense, be typical of the examples that you really care about. So sometimes it's become a natural case for this. For example, if we're predicting this peak demand from temperature, the presumption there is that we're going to use these forecasts or these predictions in the future, right? So we have some past data, and we're using this to predict what the high temperature will be in future days. So a very natural setting then would be to take, say, 1 year of data, use 1 year, previous year, as your training set, and use the next year as your testing set. It's kind of very natural, right? If you're saying, okay, you know, in reality, I'm going to deploy this for next year. Let's see how I would have done had I built my system the year before last and tested it on this year. So there are some cases where you can kind of naturally do that. But that's not always the case. Sometimes maybe there's no real temporal structure, or maybe you don't really care about the temporal structure of your data. You just want to say, you know, I just want this data as all being kind of one big pool. I just want to know how I'm going to do it. And in that case, by far the most common thing to do is just to randomly pick, say, 30% of your examples in your whole data set to be in the test set and leave the rest in the training set. So again, we have some training set, we have some set of examples. And before we were just going to say, let's just train this function on all of our examples. We're not going to do that anymore. Now we're going to select some subset of those and hold them out, take them out of our training set. And a very common split is to take 30% out for testing and use 70% for training. And do that randomly. So draw 30% out randomly to test on and train on the other 70%. Because what you're saying there, if you pick them randomly, you're saying that, you know, the exact ordering of our data, for example, when we set up our matrix doesn't matter. All that we care about is just, I'm going to treat that as kind of a representative sample of the things we care about as a whole. So 30% drawn at random will be a pretty good way of evaluating our algorithm. And this is sort of good MATLAB code to have to know. How do you actually do this in MATLAB? How do you select 30%? Well, here I'm going to let M, phi, and Y be the size of the complete data. And I'm going to generate M train, M test, which is the size of the training set, size of the testing set, and then phis for the training set and phis for the testing set, and their corresponding Ys. And a nice way to do this in MATLAB is to use this function called randperm. The reason why you have to do this, why you can't just say pick the first 70% as your examples, is that there may, in your original phi matrix, there oftentimes are some kind of implicit ordering that you didn't even really realize. Like maybe those are ordered by time. Maybe they're actually ordered inversely by time. So if you don't randomly permute your data, you're going to be a situation where you actually might be training on the future and testing on the past, things like that where you don't want to do. So a good sort of way to fix that and kind of avoid problems is just to permute your data. And this function randperm returns a permutation of m different elements there. So this lets us permute our data in a random way. And then you just select the subset corresponding to the first m train examples from phi, or the first m train examples under this permutation, and the next set of examples. And that constructs your training set and your testing set. So that's just code there that's very useful to have, and just, you know, you can just copy that from the slides. It's sort of a very useful little snippet of code to separate training sets and testing sets out in a randomized way. All right, now I want to get to, I have a little bit of time left. That's great. So now I want to get to, oh, wait, actually, sorry, before I do this, I'm going to show some examples of what this looks like here. So remember, testing error will always decrease as you increase the complexity of your classifier, add more features, take a lower regularization, lower lambda. That will only decrease your loss on the training set. The testing set, other things can happen though, right? And the cartoon to have in mind, which you'll see that kind of play out shortly, is the following. We have some notion of complexity. And when I say complexity, I mean sort of the expressiveness of the classifier itself. You know, how many features do you have? What kind of kernel do you use? What's the bandwidth of your kernel? Things like this. And then we have the performance. I'll just call this actually just the loss. You have the loss. And I'm intentionally not putting units there because this can go for any loss. It goes for any kind of complexity. What will happen on the training set is that as you increase your complexity, you'll always just get less and less loss. Right? Maybe going out to 0 eventually, maybe not, depending on, you know, the most complex model in your class. What will happen on the testing, so this one here is, this is the training set. What happens on the test set is that for very low complexity classifiers or models, these two are often pretty close. We won't discuss why they're close, but they usually will be, which kind of makes sense, right? Because if you have a very non-complex classifier, like a line, say, well, you can't really overfit to the data then. You're really going to, you know, the performance you're seeing here is really going to be a lot like the performance you get on some random news test set. And what happens is that as you increase complexity, for a while it starts performing better because you can start having a better model. But then eventually this will actually start increasing again. And this is what happens on the training set. Sorry, testing set. Good call. Testing set. Now, it doesn't always look kind of this smooth and this nice. I'll show you examples of what this really looks like now. But this is the cartoon to have in mind throughout this. Training loss always decreases. Test set will decrease for a while and then start going back up as you get too complex. So this is kind of underfitting here. Here you don't have a complex enough model. This is overfitting, where you're fitting your data and data points too much. So in our example, now we're back to our regression task here. We have our nonlinear task where we're going to predict the peak demand in Duquesne Light utility from high temperature. And we're going to do it with polynomial classifiers. Well, we're going to use nonlinear classifiers, but we're going to use them with here. We could do it with the Gaussian kernel too, but here I'm just doing it with explicit feature vectors. So I'm going to talk about adding more and more polynomial features. Here's what it looks like. So at first, a 1-degree polynomial, that's a line, doesn't do very well. A quadratic fits a lot better. Maybe by a 3rd-degree polynomial, you're doing quite well. And you sort of flatline, but this is actually improving a little bit by bit here. This blue line now is the training set. And that will keep going down. The test set starts going down at first, but then starts going back up. And I'm showing only a few here. If you go a lot further out, as you might imagine, if you fit a 40-degree polynomial to this thing, that probably is a pretty bad function. And here's what happens. I'm putting this on a log scale now so that you can actually see just how badly you do. So clearly, a 30-degree or 40-degree polynomial is not a very good fit for this. The training loss is actually really good, right? We're still fitting our data points really well in the training set. But if you evaluate them on some other random, just random subset of the data that we did not train on, they're doing very, very poorly. We have huge, huge loss there. So that's probably not what we want. We probably want to pick some point that's kind of minimum complexity that still performs well, maybe 4, degree 4 or so. Would probably be the best bet that we have here. This can help you, for example, pick which number of dimensions you want to use in your data, with one caveat on that I'll mention shortly. The same thing happens for RBFs. So if you have a number of RBFs being your input or your choice and your features, it starts doing from quite bad at first to a lot better when you have maybe 4 or 5 or 6. And then as you add more and more and more, you have the same thing. So going up to 100 now, you're again really increasing your cost a whole lot. So it isn't quite as smooth as this, because there's no reason for this really to be a smooth line in all cases. It can be bumpy. I mean, there's sort of idiosyncrasies of this data that cause it to be bumpy. But overall, it's having a very similar thing. And actually, if you averaged over a bunch of different random splits, you'd probably get something that looked a lot more like this kind of smooth line. Let's do the same thing for that lambda parameter. So remember, yeah?
The training set first needs 0.
It will eventually be 0. This data has about 1,400 examples. So it won't be 0 until you have 1,400 RBFs. I'm also plotting it on a log scale, so it stays kind of at the same spot for a while. It will eventually decrease when you get 1,400 examples. You also might have some numerical issues there, though, actually. These things get very kind of numerically unstable when you have that many different features. But yes, it will go to 0 when... Actually, that's not even quite true, because in this data, there are some days that the high temperature, at least the measurement that we have, was exactly the same. So you have a day where high temperature was 80 degrees exactly, and one day there was 1.2 gigawatt max demand, one day there was going to be 1.4. So if the training data was all different, this would go to 0. And you can think of that sort of intuitively as what it should do. But if there are duplicates in your input, then it won't necessarily always go to 0. And the same thing happens for lambda. Remember, lambda, we minimize our function, our loss function we care about, plus lambda times the norm squared of theta. That was our regularization formulation for this thing. And you get a similar thing there. So when lambda is very big, that means we're really penalizing these norms a lot. So we're going to have very low norm thetas. And as you remember from last time, or from a few times ago, that was kind of like forcing your functions to be less expressive, even if you have a lot of them, right? So for high lambda, we would expect kind of to be in the low complexity region here. And for low lambda, we kind of going to be in the high complexity region here. And the graph here looks the same. So here is the same thing for 70 RBFs, which, by the way, really overfits badly here. So 70 RBFs, if you don't regularize at all, you're doing quite badly. And as you increase theta, though, there's actually a pretty nice range here where clearly kind of this range is where you want to be. You want to pick lambdas in this range. That gives you a test performance that's close to your training set performance while still being pretty good. Okay. Yeah. So it's actually sort of inverted from this, actually, because lambda being low means actually high complexity, and lambda being high means low complexity. So it's kind of this graph in reverse here. And this is all from this real data I should mention, too. So this is really what's happening on this exact data set when I take out 30% and use 70% for testing. All right. So one last thing, which we'll talk about and we'll get to next time. This is the most common mistake people make when they evaluate machine learning methods. And it's very common even in papers to see this. Here's what I will do. Okay, I will split my data up. 70% as training, 30% as testing. I'll pick my parameters, pick the best features, run my lambda here through all the possible values. Say this one's the best one. Run all my possible RBFs. Say that's the best one. Do all these different fits. At this point, I have a training performance and a testing performance, and I just report testing performance. This is how I perform. Does anyone know what's wrong with that? Why that's actually not allowed? Right, that's exactly right. Does that make sense to everyone? Did everyone hear that? So the problem is, you are, in effect, yes, your betas you're fitting on the training set, but these other things, they're all parameters too, right? The number of features you have, that's a parameter. The lambda, that's a parameter. And you're using your supposed test set to fit all these parameters, and then you're just reporting it on that. That's the same exact thing as this reporting training error, or very close to it, in fact. Right? Because all those things were chosen based on their performance on this one testing set now. And so you can think about maybe if you have 1,000 of these different possible parameters or possible algorithms you can use, there's a good chance the best one is going to perform pretty well, even if it isn't actually indicative of good performance. So this is a very common mistake, and a lot of papers have kind of gotten very criticized for this, for essentially doing this. The tricky thing is it's very easy to do this even when you don't intend to. So let me give you the right thing to do now. And I just make sure I have time. Sorry, this is the problem. Yeah, I have a few minutes. So this is the problem, is that we're effectively using the training set, or the testing set rather, to still train the system. The thing we have to do instead is break the training set itself down into kind of its own training and testing set that we use to pick these extra parameters, and then eventually evaluate on some other test set we've held out at the first stage. And what this is called is cross-validation. So when we actually use a testing set to pick parameters in this method, we call that a cross-validation set. And so here is the correct method for evaluating algorithms. We take all our data and we break it into training and testing sets. For example, 70% and 30%. We take that testing set then in our first step, and we hide it from view forever until we're ready to submit the paper. Basically, that's what we should do. We hide it from view entirely. We just put it out of our mind completely. We take our training set now, the other 70%. So maybe I'll just draw this. So we take all our data. We split it into test and train. This throw away, not throw away, but just forget about for the time being. This one, we do the same thing. We split this again into the training set and the cross-validation set. We choose, these things are all called hyperparameters, things like the number of features, the regularization parameter lambda. We choose those all by looking at the cross-validation set. So now we're going to draw these graphs. We're going to draw graphs like this, where this is not the testing set anymore. Now it's the cross-validation set. And now we're going to say, okay, on the cross-validation set, this number right here performs the best. We're going to pick that to be my lambda. And I'm going to do all my algorithmic tuning, which algorithm to use, what kernel to use, what features to use, everything that we do, we're going to do based on this cross-validation set. We fit, and maybe once we're done with all that, once we've done everything we could possibly do, we retrain everything using the whole training set if you want to. You can then, pick your parameters and retrain all using everything. And now, just before we submit our paper, just to make sure that our results are in fact correct, we evaluate it finally on the testing set. And if performance is bad, we just give up entirely and we move on to different projects, because if we do anything else, we will have validated, or sorry, we will have invalidated our scientific process here. Now, as you can imagine, it's very easy to cheat here, right? So it's easy to say, oh, I'm going to do a lot of stuff here, all my automated stuff, but then I'm just going to look here and see how it does. Because if I don't get a good result, I probably can't submit a paper, right? So that's probably not a very good idea to do too much here until to make sure we're getting good results. And there is some element where people do this in practice, right? You almost can't help but do this just to see what it's going to look like. But it's important to keep in mind, and I'm not going to talk about specifically what exactly you need to do to be able to, what error bars you should add every time you look at this and things like that. There are ways of doing this kind of more formally. I will just say that do this as little as possible, right? Look at the testing set and never really make changes to your algorithm based on the test set performance, because doing that is just invalidates your results then. And in fact, since this is an energy course, and one of the big things that we've talked about was or motivates energy, right? And I don't want to be very careful here because personal thoughts are sort of shouldn't come into this. But one of the big criticisms about, for example, climate models is that they are doing this. They are effectively, making predictions of these models that, even though they say they aren't training on any other kind of data other than what they train on, you can't publish a paper unless it looks good on their forecasts. And so all the published models are ones that kind of fit existing data well. We don't have any other data of other Earths to test to see what would happen if we didn't release a lot of CO2 in the atmosphere. Now, this is a well-known fact, and they really try to address these things as much as possible. But these things do crop up, and they can be very, very hard. Even sort of, if you try to be as rigorous as possible, they can be very hard to completely alleviate entirely these concerns. So, don't take that as anything but just an example. I certainly don't want to talk about climate models or anything like that, because this is not what this is about. But the point is, this is the right procedure. Use it as much as you can, but just be aware of this potential problem here, that this can happen, and be aware if you end up seeing yourself doing it, because this is very important to report results that are valid in this sense. Okay, so I think we're done, or even over time, so we'll just on time exactly. So we'll pick up next time on how do we report? What numbers should we actually report in a paper? How do we know how confident we are in those numbers, etc.